speaker, which is Krzysztof Rybicki, to discuss the astrometric microlensing with the Roman Space Telescope and Gaia. And Krzysztof, can you share your screen, please? Hey.
Yes, sure.
Good to see you. And you can take it away whenever you're ready.
All right. How are the slides? They look great. Okay. Okay, so thank you, Rachel. Yeah, I will talk about astrometric microlensing in 2 satellites. One is already ongoing space mission, and the Rome one is, of course, hopefully will be flying in a few years. So, okay, so let me start with the question: why do we even care about the microlensing? It was already answered, a part of it at least. Of course, especially in the context of Roman, the main objective of this mission will be to find and characterize as many planets as possible, including planets beyond the snow line. Of course, also Earth analogs, the planets in habitable zone. Recently, very popular free-floating planets. It is even possible to detect dark matter in form of machos using microlensing, although not many mass ranges are available still. And last but not least, even black holes, not only the ones that somehow interact with their local environment, but also the ones that are completely isolated, single, and basically invisible, are still detectable using the microlensing. So at the end, did some introduction to the photometric part of the microlensing. Here I will focus on the astrometric part, because during the event, not only we have the brightening of the background source, but also the change of its position, of the position of the centroid. Here on the bottom panel, you see the change of centroid of light relative to the source position. So this effect is much more subtle than the photometric one, but it is still detectable. And in binary lenses, similarly to the photometry, it can look, it is much more complicated than for the single case. Here's just the example. So this trajectory of the centroid that has been an ellipse actually becomes some weird shape depending on the geometry of the event. Now, the thing that is important here is that astrometric microlensing gives us a direct access to theta e, a parameter that is can be obtained from photometry in some cases, as we heard from finite source effect, for example, even for free-floating planets. But in general, it is necessary to get mass of the lens. And if you're after black holes or planets, you will have to detect, tell something about the mass of the lens to claim what its nature. So it's yet another way of measuring this theta e. So let's move away from microlensing for a bit to talk about Gaia first. So this is the Gaia satellite is basically it's ongoing ESA mission now, and it was designed to produce a very precise astrometric catalog of billions of stars, actually. But it also provides photometric alerts, including alerts on microlensing events. But the thing, let me play this. The thing about Gaia is that it's a scanning satellite, not like Roman. So you see this light coming to its 2 primary mirrors from the great circle on the sky, and the Gaia precision is only very good along the direction of the scan. So its astrometry is basically one-dimensional. So now what it means is Gaia takes this on the left-hand side. We see this the general 2D trajectory of a star, no microlensing involved, just parallax and proper motion. And Gaia takes astrometric measurements from there to just one-dimensional measurement, as we see on the right. So if we take some epochs of Gaia, sparsely placed, we can have in principle scan angles distributed. Scan angles can be different in each of these epochs. So, and in every of these epochs, the shift from some reference average position is here denoted by these gray vectors. And what Gaia actually measures is projection of these shifts onto the direction of the scan. So from this 2D space, we go to 1D measurements. Now, what we did, excuse me, what we did for Gaia, we tested some of the astrometric time series on a known event, Gaia 16 AYE, which was also detected by Gaia and followed from the ground. So it was already published, it was already a known event and very well studied from the photometric point of view by Rybicki and others in 2020. But what we did, we took the astrometric series, time series, and checked if there is any signal from it visible in Gaia data. So here in the middle, on the middle panel, you can see black points, which are these one-dimensional Gaia measurements, and two models, the blue one without microlensing and the red one with microlensing. And on the bottom panel, you see the residuals of these two models. So you see that the standard model without including microlensing is actually working, not working very well. It can't really describe the data that we have, especially in the here during the caustic crossing, where not only the photometric changes is large, but also the astrometric one. So let me play this out. Is it moving though? Can you see the animation? Sorry.
Yes.
It does move.
Yes, it is moving.
Okay, cool. It's very laggy from my side. Anyway, you see the you see that during the on the right panel, you see the how caustic is changing during the changes in projected position of components of the lens. Now in blue, in blue there is a source trajectory, and in red the centroid of light trajectory, which of course changes during the event. And well, we were able to, basing on this one-dimensional data, we were able to reproduce the theta e and mass of the lens, as was already done from the photometry alone. So this is just an example that astrometric microlensing can be detected and will be detected in Gaia. Okay, I hope it worked. So moving to Roman, we did also experiment on the very basic level with the data from generated data from Roman Space Telescope, using all the assumptions about the data that were already described before. So the 15-minute cadence and 3 seasons at the beginning and end of the mission, and also the accuracy of photometry and astrometry based on the simulations that were shown yesterday by Sebastiano. So what we did, we basically studied 2 classes of events, which are the normal standard ones with a regular lens of less than solar mass, basically a dwarf, and something we are more after, so isolated black holes with example mass of 8 solar masses here. So here I'm showing 3 panels with photometry, and bottom and top panels are astrometry, this time of course 2-dimensional. These are just 2 components, north and east. And you see that even for dwarf, the signal is clearly there from the measurements of Roman. So so what we did here is the slightly different representation with the on-sky trajectory. So not only the signal from astrometric microlensing, but also proper motion and parallax. And you see that the signal is obviously there, much larger for black hole, but even detectable even for a more normal lens. So we did model this, did feed the data to such motion curves, and we did reproduce the input parameters, the input mass, most importantly, with accuracy ranging from few percent to 10 to 15% for lighter lenses. So this is the comparison of the two.
Remaining.
Okay, thank you, Rich. So this is the comparison of the two missions, and just one example event for Roman and Gaia. Gaia moved to 2D space. As you can see, these gray error bars are across scan directions. That's why they are so large. This is basically almost one-dimensional measurement. So obviously Gaia was not designed to measure transients. It was built to produce the astrometric catalog, and Roman will be staring in just one field of view. So and not being a scanning satellite for the whole sky can have exposure time tweaked properly, unlike Gaia. But the biggest difference here is the cadence. So Roman will have continuous measurements for the events with 15 minutes cadence versus average 30 days cadence for Gaia. So obviously we will have large step forward here for Roman. So this was my last slide. This is the summary and takeaway messages I wanted to have. So basically, the most important is that Roman is actually looking very good in terms of astrometric microlensing and its potential in that field, and it basically will be game changer from few events we have here. Maybe we will have few more to probably hundreds after Roman. And Gaia already does that on the smaller scale, but it is possible, as you have seen. So we may be able to measure theta E even for lenses that are invisible. So I stop here. Thank you.
Thank you very much, Krzysztof. Excellent talk. And I see we have a question already from Will Dawson. For the dwarf and black hole simulation examples, did you do a fit to the simulated data? If so, how tight were the priors on the lensing parameters? We've found that in the past, when we have gaps in the data, there can be large uncertainty in what the parallax is. And he compliments you on a very nice talk.
Yeah, thank you, Will. So these were just examples. We did. The process of fitting itself will for sure have to be rethinked or actually designed properly. So these were just simple fitters like using MCMC and some simplex fitting, starting in random places of the parameter space. And for example, for these cases, it was because you can approach to the fitting in multiple ways. You can, for example, here we were fitting all the parameters, including all the proper motions of both source and the lens. You can try or think of the case where you will know, for example, proper motions of the source prior to the event or to the Roman itself, even as we heard from Etienne with some additions of other missions. So in this case, you can maybe try to fit only centroid motion due to astrometric microlensing, and then it should be easier. Or another thing you can think of having multiple classes of events. For example, those that have very good photometric light curve covered, and then you would use priors based on photometric models on the astrometry before doing the astrometric fitting. And on the other hand, you can have events where there is no photometry at all, and you will have only astrometry. So I don't know if it answered your question exactly, but I'm looking at the question now. So the priors were not really closely looked into.
Thank you, Krzysztof. And I noticed that there is another question for you in the Slack thread, but in the interest of time, we're going to move the presentations on. So if you kindly answer that in Slack. And thank you, Krzysztof, once again.